Bismillahirrahmanirrahim. My name is Adil Ihsan and I am presenting my final year project, which is robust control of a quadrotor and active disturbance rejection control approach. This project is supervised by Dr. Jamshed Riaz. Here are project objectives. Quadrotor has caught significant attention because of its simple flight mechanics, agility, and hovering capability. Due to increasing applications and uses of multicopters, their performance requirements in different conditions are becoming more challenging, which require better designs and robust control strategies. Lately, PID being simple and effective has been used in process control industries as well as aerospace industry. However, the limitations of PID and the rising requirements of robustness, precision, and efficiency has driven engineers to look for better control strategies, and ADRC has come out to be a better and more reliable alternative. In this project, a robust flight controller known as linear active disturbance rejection control is proposed for a control of a quadrotor. ADRC is a model-independent nonlinear robust control technique. Its main idea is to group all disturbances, foreign and internal, into a single disturbance term and then estimate the effect of this disturbance in some accurate manner and then finally devise the means to cancel its effect using gathered estimate as a part of feedback control action. At first, mathematical modeling of a quadrotor was done on the basis of Newton's second law and then a linearized model was derived. Since the aim of this project was to compare PD and LADRC, thus at first both controllers were designed for a nominal linear model and then implemented on a nonlinear 6-degree of freedom simulation. After that, both controllers were discretized and then MATLAB level 2 S-function code was written for each controller. The S-function codes for both controllers were then validated and implemented on a nonlinear simulation. Here is the 3D path tracking response of a quadrotor with both controllers. This is the corresponding individual position responses. This is the response for the linear velocities. And this is the response for the angular rates. These are the corresponding Euler angles. And finally, this is the plot for the control actuation, which is RPMs of the motors. After that, performance of both controllers were tested for disturbances in a linear model, and here are the responses of both controllers with step input disturbances in attitude and altitude channels. These are the responses of both controllers for altitude and attitude channels with uncertainties, and there is overlapping in LADRC responses while there are fluctuations in PID responses. Then both controllers' performance was evaluated with disturbances and uncertainties in a nonlinear model. Here is the response for the disturbance in height channel and corresponding control actuation generated by each controller. And we can see LADRC brings system back to its original position. This is the response for the disturbance in pitch channel and corresponding control actuation generated by each controller. And again, LADRC brings system back to its original position. This is the response for the disturbance in yaw channel and corresponding control actuation generated by both PD and LADRC. PD controller designed earlier was then implemented on an APM 2.8 hardware, and here is the flight test video. We can see that quadrotor is quite accurately following the RC channel input. The quadrotor was flown in an altitude hold mode, and we can see that it is holding altitude quite accurately. These are the flight test results for the PD controller with APM 2.8 hardware. After retuning both controllers for Parrot drone parameters, the PD controller was implemented on a Parrot drone, and here is the hover flight test video. And we can see that quadrotor is quite accurately following the reference input. These are the flight and simulation results for 3D path tracking of a Parrot drone with PD controller. Then LADRC was implemented on a Parrot drone, and here is the hover flight test video. And we can see that LADRC implementation was quite successful on Parrot drone. These are the LADRC hover flight test results, and we can see drone was quite accurately following the reference input. LADRC being model independent has numerous industrial applications. This concept can be applied in mechanical, electrical, and chemical industries where we do not have accurate mathematical models. Here are some remarkable results achieved with LADRC. A leading provider of servo drives tested ADR control on a variety of motor drive configurations, and some of the findings are below. 81% reduction in maximum position error, 41% reduction in RMS torque, and 71% reduction in jerk. ADRC has been running a house extrusion production line for over 6 months and resulting in over 200% increase in product quality and 58% reduction in energy consumption. A lot of research work can still be done by testing ADRC on aerospace vehicles. It can be implemented on rockets and spaceships. It can be implemented on autonomous vehicles on other planets. It can be used as a control strategy for attitude control system of satellites, and it can be used for docking crew station with International Space Station. Finally, it can be concluded that this method provides an alternative design framework in solving industrial control problems without the need for an accurate mathematical model. It is shown that ADRC has strong disturbance rejection ability and it is highly robust. Thanks for watching the video.